अच्छा चलिए ठीक है, लेट्स स्टार्ट ऑर्गेनिक से स्टार्ट करें एंड उसके क्वेश्चंस जो है ना वो यहाँ पे दिस इज 28 1 सेकेंड। अच्छा रिमेंबर W19 है, ठीक है ये। अच्छा क्वेश्चन नंबर 20, that's where organic questions usually start with. तो होपफुली अगर नजर नहीं आ रहा ना तो मुझे जरूर बता देना। So starting
Start with
with वालेकुम सलाम। अच्छा starting with this one, question number 20 वो कह रहा है कि uh, draw the structural isomerism and stereoisomerism should be considered when answering this question. How many isomers with the formula C5H10 have structures that involve pi bonding? ठीक है, so इसके ऊपर थोड़ा टाइम जाया कर लें कि you have to draw first thing. Remember always to focus on structural isomers and then find which one out of them are making stereoisomers. And pi bonding, that means double bonds. So C5H10, one of them would be all 5 carbon atoms. I think there's no other condition that's given except it has to have a pi bond. So that means it has to have a double bond. So 5 carbon atoms, the double bond could be, how much is that? That's 4 plus 5. So the double bond could be on the first carbon atom. The other variation or version of this would be that the double bond can be on the second carbon atom. Okay. Now, in a straight chain, that's it. Okay. You can't move the double bond anywhere else because then it's going to be the same arrangement. It's just going to be a flipped. Like if I put a double bond over here, then it's going to be pretty much the same thing. It's going to be pretty much the same thing, except that it would be a flipped version of this same thing. Okay, so if I put a double bond here, it's still going to be the same thing. So then I'm going to move towards branched hydrocarbons. So it's going to be 4 carbon atoms, and I can have a carbon over here. And where do I put the double bond? I can put a double bond on the first carbon atom. Now, putting a double bond over here or over here kind of means the same thing. Okay, make sure. Like if I had added the double bond on this point, that would pretty much be the same thing. It would be exactly the same arrangement. So that's one. The other place I can put the double bond is in the same arrangement is on this carbon atom. And the third place I can put a double bond is using the same arrangement of carbon atoms. That's going to be this one over here. Remember, all 3 are different. Over here, I mean, along this carbon atom, there were 2 branched carbon atoms, so you can put a double bond at any one of those. You could put a double bond between, right in the middle, or on the other side. So that's 3. Then again, you've got 5 carbon atoms, so there's going to be one more arrangement, and that would be where do I draw this? That one could be that there could be 1 carbon atom in the middle and 4 carbon atoms on the sides, and you can have a double bond over here, but that is not going to be possible. And the reason that's not going to be possible is that if I do that, then the carbon atom would be making 5 bonds. So this one is not possible. So I think we are stuck. I can't have 2 branches. We're stuck with these 2 arrangements of carbon atoms. So there are a total of 5, 1, 2, 3, 4, and 5 structural isomers. Now I need to figure out the total isomers, including stereoisomers. Whenever you have a double bond, the only thing that's possible is you can have cis trans. For cis trans, you need the double bonded carbon atom to be bonded to 2 different groups. So the first one, that's not going to form cis trans. The second one is going to form cis trans. Why? Because the double bonded carbon atoms are bonded to 2 different groups. I mean, this one is bonded to 2 different groups, and this one over here is also bonded to 2 different groups. On one side, there is CH2 and CH3. So that is 2 different groups. So this would be counted as 2. There's going to be a cis version and there's going to be a trans version of this molecule. And just for the sake of clarity, the cis version is going to look like this. Around the double bond, if I draw one of them, around the double bond, the carbon is fan-shaped. So the three-dimensional arrangement would be that around this carbon atom, there's an H and a CH3. So you can have an H and a CH3. And around this carbon atom, there's an H and a CH2, CH3 ethyl branch. So there's an H and there is a CH2 and CH3. This would be your cis version. And there's going to be another one that's going to be your trans version where the H and CH3 are pointing in opposite directions. The CH3 is pointing upwards, the H is pointing downwards. And anyway, so this one will be two. There will be two versions of this. One would be cis and one would be trans. DK, is this clear? Hania, is this clear? Hadia, Nihal, is this clear?
Yes, sir.
Achha, next one is you've got this one. Again, no cis trans because the carbon is bonded to two hydrogen atoms. And then you've got this one. Again, there's no cis trans. That the carbon is bonded to two hydrogens. So there's not going to be any cis trans. Then you have the last one. This is also not going to form cis trans because this carbon is bonded to the same groups. There's CH3 on this side and there's a CH3 on this side. So again, the carbon is bonded to the same types of groups. So I'm going to total all of this now. It's going to be 1, 2, 3, 4, and this would be 2. So there would be cis and there would be trans. So that's going to be 5 and 6. So that's going to be our answer for this one. And remember, this would be counted as 2. Okay, there's going to be a cis version and there's going to be a trans version. Next one is the diagram shows the skeletal formula of phenazine and what is the empirical formula of phenazine. So you have to count the total number of carbon atoms. So that's 1, 2, 3. I mean, there's 6 carbon atoms in this ring, and there's 6 carbon atoms in this ring. So that gives you a total of. Remember, in a skeletal formula, every node is a carbon atom. So that's 6, and there's 6 over here. So you've got a total of 12 carbon atoms, and there are 2 nitrogens. So that's N2, and the only challenge now left is counting the number of hydrogens. So I'm going to mark, there's going to be 1 hydrogen here, 1 over here. Each carbon should be making 4 bonds. 1 over here, 1 over here, 1 over here, and 1 over here. I mean, each of these carbon atoms in the ring, that's already bonded to 3 atoms. So it's already bonded to 3 atoms. That's the 4th hydrogen. This carbon is already making 4 bonds. This one is also making 4 bonds. This is 4 bonds, 4 bonds. So all the rest of the bonding is kind of complete. Nitrogen is supposed to make 5. Sorry, it's in group 5. So it's supposed to make 3 bonds, which it is making 3 bonds. So that's it. That's 4 hydrogens here and 4 hydrogens over here. So that's a total of 8 hydrogens. And you can now just divide everything by 2. It's going to give you C6. N would become 1 and H would be 4. Which is why I think option A is the correct one. Okay. So option A is the correct one in that case. As a next one, you've got, is this clear?
Yes, sir.
So then you have on an organic compound X reacts with hot concentrated KMnO4 solution to give a single carbon containing product. So single carbon containing product. First thing, whenever you have hot concentrated KMnO4, that is usually a condition for alkenes, oxidation of alkenes. In oxidation of alkenes, you have the double bond is going to break. Okay, that's going to break completely. And each of these carbon atoms which were making double bonds, they will undergo some sort of change. So if that carbon atom is bonded to 2 hydrogens, then it's going to change into a carbon dioxide and a water molecule. If that double bonded carbon atom is bonded to just 1 H, and on the other side, there's a carbon chain, which I'm going to call R. So that would turn into, I mean, that particular carbon would turn into a carboxylic acid. It would become serial bond O and OH. Okay, the third one is you've got double bond carbon. And on both sides, so that's going to give you a ketone. So 3 different oxidation products. So he's saying it's only going to give you 3 a single carbon containing product. So let's start with the first one. It's now they didn't tell you where the double bond is, so you have to figure that out on your own. The first one is CH2. Then there's a C, and that C, there are two CH3 branches attached to it. Okay, so there are two CH3 branches attached to it. Now, according to this, double bond has to be over here because the carbons are not making making 4 bonds. So the double bond are probably going to, the double bond is probably going to be here. I said that's not going to give you one product, because if the double bond breaks, this carbon will turn into a carbon dioxide molecule because it's bonded to two H's. So that's going to give you carbon dioxide. And this carbon atom over here will turn, because it's got two carbon chains, that's going to turn into a ketone. So this one, the CH3, it's got two CH3s. So that would probably turn into a ketone. So again, you've got two different products. The second one, B, is going to be your correct option, because if you draw this, it's CH3, then there is a C with an H, and then after that there's another CH, and after that there is another CH3. The double bond has to be here. So the double bond is going to completely break. Both sides are identical. So even if you don't figure out what the product is, both sides are identical, and they will give you the same thing. They will give you a single carbon containing product. This one will give you ethanoic acid, because if there's one H with the carbon that's making the double bond and one carbon chain, it's going to turn into a carboxylic acid. So this particular carbon atom will turn into carboxylic acid, and this would become double bond ONOH. और यही चीज ना, the same thing would happen to the other one, which is this one. So that will turn into a carboxylic acid as well. So this is the correct option. Option C is, so just for the sake of practice, we'll just do option C as well. It's got CH2, and then there's a CH. If you look at C, there's a CH, then CH2 and CH3. So that is CH2, and you've got a CH3. Now the double bond is going to be here. So if it breaks during strong oxidation, this will turn into carbon dioxide and H2O. And this one will turn into a carboxylic acid. It would become CH3, CH2, and C double bond O and OH, because it's got one H. If the double bonded carbon atom has one H, that would give you carboxylic acid. And the last one will not have any oxidation because it doesn't have any double bonds. If you draw this, there is no double bond, so there's not going to be any strong oxidation. As anyways, that's going to be B. Okay. Is this clear?
Yes.
So next one is this one. It's a reaction of 1-chloro-2-methyl butane reacts with sodium cyanide in ethanol in a nucleophilic substitution reaction. What is the most likely intermediate or transition state in this reaction? First thing, what's happening? It's a halogenoalkane. Okay, so just a brief recap of what a halogenoalkane is. It's a butane. Okay, they've already told you it's a butane. So butane is 1, 2, 3, and 4 carbon atoms. On the second one, there's a methyl. So the second carbon atom, there's going to be methyl, which means there's 1 carbon atom. And there's 1 chloro. So on the first one, there is a Cl. So over here, you have a Cl, and we can add in all the hydrogens. So you got hydrogens here. This one has hydrogens. This one has 2 hydrogens. This one will have 3, and this one will have 3 hydrogens. Now, the first thing is you need to figure out, whether it's a primary halogenoalkane or a secondary or a tertiary. So I'm just going to give you a brief overview of all of this. This one over here is, this carbon atom over here, that is a primary halogenoalkane, because whenever carbon is bonded to just one carbon chain, it's bonded to a carbon chain on one side, not one carbon chain. Obviously this is not one carbon chain, but it's If the carbon is bonded to a carbon chain on only one side, and on the other two sides there are hydrogen atoms dashed, then that's a primary halogenoalkane. And the story behind, and the other one is, I'll just briefly give you an overview of a tertiary halogenoalkane after this. Let's focus on primary halogenoalkanes. Now the story with primary halogenoalkanes is that when you have a primary halogenoalkane, the carbon is not surrounded by carbon chains. Remember, carbon chains have this effect. The CCl bond is polar, chlorine is partial negative, and the carbon over here has a strong partial positive charge. So the carbon is bonded to fewer alkyl chains. Alkyl chains have this electron donating effect. They're going to push the electrons. I mean, alkyl chains have lots of electrons. The hydrogen atoms, they don't have a lot of electrons. So if the carbon chain is surrounded by mostly hydrogen atoms and fewer alkyl chains, like in a primary halogenoalkane, there's only one alkyl chain, then the electron donating effect is very slight, which means that the positive charge is going to be very large. It's going to be a very strong positive charge, which is why what's going to happen is that, and let me just be very clear, that this carbon has a very strong positive charge. And the reason behind that is that it's surrounded by just one alkyl chain. There's only one alkyl chain here. And on two sides, there are hydrogens. So it's not surrounded by a lot of electrons. If there was a carbon chain on this side and there's a carbon chain on the bottom side as well, then the positive charge would diminish. It would slightly decrease. But at the moment, it's going to be very large because there's only one alkyl chain. So if the positive charge is really strong, what it does is that if there's a nucleophile, and there could be three types of nucleophiles. You could have an OH ion, you could have an NH3. They all have these lone pairs. In this case, we are talking about Cn-1. We're specifically talking about the cyanide ion. The Cn-1 will be very strongly attracted to this carbon atom. So it's going to be very strongly attracted to this carbon atom, and the Cn-1 will try to bond with it. So what's going to happen is there's going to be, carbon would be partially bonded to 5 atoms in between, like the Cn would be approaching and the Cl will, because of the negative charge over here, the Cl would be getting repelled. So it's going to be something like this, that there's going to be an H, there's an H here, there's an H here. On this side, there was this carbon chain, which is, I can compress that, it's CH, there's a bracket, CH3, there's a branch going downwards. Then you've got CH2 and you've got CH3. On this side, you have a Cl. And there's a Cn-1, and I just told you that the positive charge is really strong. It's a very polar bond. The Cn-1 will immediately start getting attracted to, or very strongly it will get attracted to the carbon, which is over here. And as the negative ion comes closer to it, the Cl starts getting repelled. So the bond will slightly break. It will start leaving. So the Cn-1 will start approaching and the Cl would start leaving this. So both of these structures, I mean, the first one, I mean, the bottom two are obviously wrong. And this is called an SN2 mechanism. Primary halogenoalkanes, they always have an SN2 mechanism. The nucleophiles, they directly get attached to the carbon atom. When you have an SN2 mechanism, whenever you have a primary halogenoalkane, the positive charge is really strong, and your nucleophile directly gets attracted to the carbon over here. Is this clear to everyone?
Yes, sir.
Okay, Nehal, is this clear?
Yes, sir.
Achha, so the bottom two are C and D are obviously wrong. So what is the most likely intermediate or transition state? You don't have intermediates in primary. You have a transition state. There's a transition that would be happening. Cn would be approaching and the Cl would eventually leave. So basically the Cl will get substituted. So which is why it's substitution and it's nucleophilic.
सर ये साथ-साथ होगा या पहले एक रिमूव होगा फिर दूसरा?
नहीं साथ-साथ होगा, ठीक है? This is happening simultaneously. Remember the positive charge is really strong, ठीक है? वो clear है ना बात?
Yes, sir.
क्योंकि उसको कम करने के लिए कोई है ही नहीं, there's no alkyl chains around it, ठीक है, there's just one, ठीक है. So the positive charge is really strong, so it attracts the CN very strongly, so it starts getting attached to it, and simultaneously the Cl starts breaking away. Eventually the Cl will get pushed away and the CN will take its place. So during the transition state,
Cl ज्यादा electronegative नहीं?
हाँ, तो इसलिए it's going to pull the electrons and take the electrons with it, ठीक है. अच्छा, so क्योंकि Cl wanted to take the electrons, मतलब which is why Cl was partial negative. वो Cn-1 helped it. It came from the other side, and remember the attack always happens from the opposite side. If the Cl is over here, the Cn-1, because both ions are negatively charged, okay? So when you draw the mechanism, even in your paper twos, when you draw the mechanism, the Cn-1, if the Cl is on this side, the Cn-1 should attack from the other side. Okay, is that clear?
Yes.
But ये draw नहीं करना, ठीक है? If you don't draw this one, के Cn-1 is attacking from this side, that can be marked incorrect because both negative ions will not be on the same side. Okay, so it's just a minor point, but remember, just be very careful. The Cn-1 or the OH-1 or the NH3, they would be coming from the opposite side. As anyways, so which one? I've drawn the transition state. I just need to figure out which one is the correct one. So it's there's a carbon atom and there are two H atoms attached to it. So it's probably this one. It's I mean, the middle carbon atom, it has two H atoms attached to it. I mean, because this one is going to be incorrect. The middle carbon atom had two H atoms, so it's going to be A. Okay, and then there's a CN attached to it, a Cl partially attached to it, and on the fifth side there's a carbon chain which is CH, CH3, CH2. So it's going to be A for this. I'll also do tertiary halogenoalkanes just for the sake of revision. The conditions for this. For Cn-1, you have NaCN ethanolic. For OH-1, you have NaOH, which is aqueous. For NH3, it's ethanolic. NH3, or it's going to be NH3 gas in a pressurized sealed tube. In all three cases, you heat. You reflux, and for NH3 ethanolic, you also reflux. But if it's a gas, then you just heat it. The other thing is about tertiary halogenoalkanes. Now, in tertiary halogenoalkanes, now what happens is that the carbon on which the Cl is bonded to it, the bond is still polar. So I mean, that's the partial positive and negative charges are still there. Except that carbon is not going to have a very because there's going to be more electron donating effect. So carbon is not, I mean, lots of electrons around it, lots of carbon atoms, lots of alkyl chains around it. So the positive charge is not going to be very strong, which is why the thing is that the Cn-1, any nucleophile, whatever the nucleophile is, it's not going to be that strongly attracted to it. There's not going to be that strong an attraction. So what happens in this case is that you wait for the Cl to break on its own. Like Cl wants to gain electrons, but the positive charge is not strong. So there's no push coming from the other side, like in the previous case. I mean, the Cn-1 are not getting attracted to the positive charge, which is kind of small here. So you would have to wait for the Cl to break. So there's going to be a very slow step. The first step is going to be very slow because you would have to heat it. You would have to increase the number of collisions. And then maybe during those collisions, the Cl might break off. So there's going to be a very slow first step. And a carbocation is going to be formed. The Cl, after a very slow process, after waiting for a very, very long time, during a collision, the Cl might break off and a carbocation would be formed because the Cl would take its electrons. This carbocation is going to be very stable. And so this is, so it's going to be very stable, and the Cn-1 and the C with its lone pairs will now get attracted to the positive carbocation, and that would result in the formation of the substitution product, which is the Cl will be substituted by Cn. Now you often get a question why. I mean, I've given you all the explanation, but what are you going to write in your exams? That why do tertiary halogenoalkanes they go through this mechanism? I mean, there's a slow step, and after that there's a fast step. I mean, the second step would be fast because you have a positive carbocation and you have a negative ion, so they will attract each other immediately. The explanation for this is, I mean, all of this that we talked about, the way you're going to state in your exams is that if they say, why does tertiary halogenoalkanes follow this route? The simple answer is, it's got a more stable carbocation. That's it. I mean, you don't have to like explain everything. Just tell them it has a more stable carbocation. And why is it more stable? Because it's got more alkyl chains. As it has more electron donating alkyl chains. So that's it. Okay. This is what you're going to write in your paper. You put your explanation and this would be summed up using this. Okay. Is this clear?
Yes.
And if they ask you why this is following this route and why is it not making a carbocation, because it's got an unstable carbocation, because it's got fewer alkyl chains. So the positive charge that would appear would be so strong that it will not let the Cl go away. So the Cl will keep on sticking to it until and unless the Cn-1 pushes it away.
So two alkyl chains में क्या होगा?
हाँ, वो बीच वाला, that's the middle one. That's the middle one, and that could go either way. For that, it depends. It depends on the reaction conditions, etc. So it could go either way. It could be SN1 or SN2, or it could be a mixture of both. For example, if you have two alkyl chains, that's the middle one. That's the secondary halogenoalkane. In that case, what might happen is that if the reaction temperature is very high, then during collisions, there would be a very good chance of the Cl breaking off. And if the Cl breaks off because of the higher temperature, there would be a greater chance of the carbocations getting formed. Do you get this point?
Yes, sir.
And if the reaction temperature is not very high, then there would be very less. So it will depend on a lot of things, on reaction conditions, on the type of molecule. So remember, secondary, that's a mixture of SN1 and SN2. Okay. Is this clear? Nucleophilic substitution of halogenoalkanes.
Yes.
So now next one. That's about oxidation of alcohols. Remember, that's very important. I'll just let's quickly go over that as well. And that's something that's very important. You have to remember that primary alcohols, they get oxidized, they turn into aldehydes. And then if you further oxidize them, they turn into carboxylic acids. Then you've got secondary alcohols. Secondary alcohols, they turn into
Ketones.
Okay, secondary alcohols turn into ketones. And tertiary alcohols have no oxidation whatsoever. Okay, उस case में there is no oxidation. इस को आवाज क्लियर आ रही है? कोई इशू तो नहीं है?
नहीं सर.
ठीक है. अच्छा, so primary alcohols, they turn into aldehydes and then carboxylic acids. Now the reaction conditions for this one, it can be K2Cr2O7 acidified and reflux. And you can also use KMNO4 for this, which would also be acidified and reflux. This one is the same. Okay, so
ये H plus क्या? H plus.
acid. मतलब वो एसिड बीच में ना ऐड करना है, ठीक है। अच्छा एनीवेज ये भी दिस वुड बी द सेम, ठीक है, एंड सेकेंडरी alcohols that would also be the same. So all three kind of have the same conditions. Now, except and reflux. Except aldehydes have other oxidizing agents that can work with them as well. So aldehydes have three. There are three things that can actually do that. That can turn an aldehyde into a carboxylic acid. The second one is going to be your Tollens reagent, which is Ag and NH3 twice, and it has a charge of +1. It's basically Ag+1. And the third reagent, same cheese, aldehyde turning into a carboxylic acid. So that's aldehyde turning into carboxylic acid. Number 3 is Felling, which has copper 2+ ion. It's also known as Benedict solution. It's a blue colored solution. So all three will turn an aldehyde into a carboxylic acid. And you should know what an aldehyde is. Aldehyde is serial bond O, and it's got an H atom, and carboxylic acid will have an additional oxygen atom, which is why this is oxidation. So you have
ये तीनों का बताना जरूरी है, all three reagents.
हाँ ये बहुत important है, ठीक है। अच्छा anyways, so all three, any three, including KMNO4, not just the reagents, you should also know. In the case of Felling, you would also be heating it. Okay. And not only that, what also that needs to be understood is what are the color changes. In the case of Felling, you get a red precipitate, or specifically a brick red precipitate. In the case of Tollens, what you get is a silver mirror. Silver has this on top of the solution, and there are two observations actually. You get a silver mirror and you get a black precipitate as well. Usually you get marks for writing just one. So silver mirror plus black precipitate. What happens is that all of them, they get reduced. Felling gets reduced from copper 2+ to copper 1+. So the copper 1+ oxide that's formed is brick red in color. Silver ions, they get reduced to silver. So on the top of surface of the solution, you have this shiny layer that is formed, which is very reflective. K2Cr2O7, hopefully everyone remembers, that's orange to green. KMNO4, that's purple to colorless. So remember the conditions of each one of them. Then there are a few more things, and those few things are that if you want this reaction to stop at aldehyde, and you don't want it to get oxidized to carboxylic acid, how do you stop here? The way you can stop at this point is, instead of reflux, use distillation. Now, if you know what reflux is, or heat with reflux is, reflux doesn't allow things to escape from the flask. I mean, this is what a reflux. One second. So that's how a reflux condenser works. You're basically trying to heat the substance, but if the substance is volatile, it's going to evaporate. So you don't want it to evaporate. So you put a condenser on top. The condenser is just there so that nothing is able to come out of the flask. So the reaction will go to completion if there is reflux, because nothing can escape when it's a reflux. So whenever it's reflux, the primary alcohol will turn eventually into a carboxylic acid. It will not stop here because nothing can escape the container, and the reaction will go to completion. But if you allow the product to escape, you use distillation. In distillation, you use the condenser. I mean, distillation is something else. Distillation is distillation has this apparatus. when you allow you're heating it, but you're allowing the product to escape. You're allowing it to evaporate and condense somewhere else. So in that case, the reaction will stop at aldehydes, because as soon as the aldehydes are produced, the aldehydes will evaporate, and if they evaporate, you can collect the aldehyde to the in the other conical flask and separate it from the rest of the mixture. So the aldehyde will be saved from getting oxidized to carboxylic acid. So if you want to stop at aldehydes, you use reflux instead of, you use distillation instead of reflux. And they might ask you, they have actually asked you about this in past paper as well, that why does the reaction stop at aldehydes? Because carboxylic acids have OH, alcohols also have OH groups. They have hydrogen bonding. They've got slightly higher boiling points. Aldehydes don't have hydrogen bonding, so their boiling points are slightly lower. They're more volatile. So as soon as they are formed, they quickly evaporate, and you can collect it at the other end, and that way the aldehyde will not get further oxidized to a carboxylic acid. Is this all clear? Everyone, is this clear?
Yes, sir.
Okay. There's another thing, and that is you have to know the opposite as well, the reverse. The reverse is reduction. So the same thing could be reduced as well. You can go back from carboxylic acid to aldehydes. In that case, you'll use LiLH4, which is your reducing agent. And the aldehyde could be reduced to primary alcohol as well. In that case, it's going to be NaBH4 or LiLH4. And ketones can also be reduced back. So if you reduce a ketone, again, it's going to be NaBH4 or LiAlH4. Now, this entire thing, this chart is one of the most important things. You need to know what happens when alcohols are oxidized, what happens when aldehydes get reduced, what are the observations, etc. So you need to know everything about oxidation. So this is oxidation of alcohols. You also need to know about the oxidation of alkenes, which we just studied. So I'm going to go back to the question.
ये जो आपने बताया ये रिवर्स रिएक्शन के लिए
हाँ, ये जो ब्लैक में लिखा है ना, that's for the reverse.
सही
ठीक है. LiLH4 and NaBH4 LiLH4. ठीक है. अच्छा, then you've got किधर गया question? अच्छा, this one. So remember, this is a primary alcohol. I mean, you should be able to identify it's a primary alcohol because when carbon is bonded to two H's and just one carbon chain, that is a primary alcohol. So he's saying it can be reacted with potassium dichromate 6 to form propanoic acid. So I think it's forming propanoic acid or propanol reaction number 2. So it's getting oxidized. So he's saying the primary alcohol, where did we go? So he's saying that the primary alcohol will turn into an aldehyde. And remember, I just told you about this. And he's saying the primary alcohol can be turned into a carboxylic acid. The only difference is, if you want it to stop at aldehyde, you don't do reflux, you do distillation. And if you want to go all the way to carboxylic acid, then you do reflux. You don't allow anything to escape, and you'll eventually end up at carboxylic acid. So this question is about that. Okay? So he's exactly asking this. So he's saying, how can the reaction be carried out to ensure that reaction 2 occurs rather than reaction number 1? Reaction one goes all the way to carboxylic acid. So that is reflux. Nothing can come out of the container. That's reflux. Reaction number 2, it's going till aldehyde. So that means you're using distillation. So how can the reaction be carried out to ensure that reaction 2 occurs? So C is distilled immediately after mixing. So that's correct. ठीक है. So now the next one is what is the smallest amount of oxygen molecules? You clear है सारों को पिछला? Right? Yes or no? Is this clear?
Yes.
Yes.
So next one is, what is the smallest amount of oxygen molecules needed for the complete combustion of 40 grams of methanol? So it's a moles question. So complete combustion. So methanol is CH3OH. So let's quickly do this. It's going to be reacting with oxygen. So I think it's complete combustion. So CO2. And he's saying the smallest amount of oxygen molecules, which is basically as a CO2 and H2O, it's going to be 2H2O and they're 4 oxygen. So there's going to be 3 by 2, 1.5. As anyway, so you've got 40 grams. You can find the moles. 40 divided by the MR. The MR of this would be CH3 is 15 and 17. What's that? 32. Can somebody double check this? 17 and that's 12 plus 3. That's 15. 15 plus 17 should be 32. So those are your moles. So 40 divided by 32. Can anyone tell me what the value is?
1.25.
So 1.25 moles. So it's 1:1.5. So how many moles of oxygen? 1.88.
जी सर 1.88
ठीक है तो 1.8 खैर ये तो बहुत ही बेसिक क्वेश्चन आया था देख लो कोई इसमें कोई ट्रिक तो नहीं है इस पे शक हो जाता है कि इतना आसान क्वेश्चन है What is the smaller amount of oxygen molecules needed for the molecules? ठीक है सारे वो देख लो atoms की बात तो नहीं कर रहा ठीक है I think that should be the answer. As anyways, next one. ये Felling का आ गया ठीक है we just did this. Compound X has stereoisomers and forms a precipitate when warmed with Felling's reagent. What could be the structure of X? As the first thing, Felling. Who reacts with Felling? So who reacts with Felling? Aldehydes. They get oxidized with Felling. Red precipitate, brick red precipitate. So kahan gaya? So and he's also said that so aldehyde. This is gone. This is not an aldehyde. Okay. This is fine. This one is fine. So दो तो निकल गए बीच में, so they're not aldehydes. Okay. That's. I mean, both of them are ketones. For aldehydes, the double bond O should be right at the end. Over here, the double bond O is also right at the end. Okay. So they, तो A or B. ये वाला part तो हो गया. ठीक है, we're done. इसने दो को निकाल दिए. The other one is compound X. So now the other part is compound X. नहीं A कौन सा type का stereoisomer होगा?
B होगा.
Cistrons.
नहीं, it can't be cistrons क्योंकि ये जो carbon atom है ना, it should be bonded to two different groups. Over here, you have the same groups. Is this clear?
सही.
ठीक है, so I mean this will not form cistrons. So it's piece option. The only option left is D because it's going to have an optical isomer. This carbon atom, I mean, there's going to be one H. Okay. So the H is not shown. All four sides are different. On one side, there's an aldehyde carbon chain, another carbon chain, and an H on one side. So that is going to have two mirror images, non-superimposable. Clear?
Yes, sir.
As a diagram shows the structure of Y, and it's a ketone. It's a double bond O is in the middle. So two suggestions are made about Y. Remember, it's a ketone. Y can be oxidized by dichromate 6 ions. Is that true? Ketones, can they be oxidized? Ketones.
No. Oh.
Remember ketones, that's where the oxidation ends. I mean, after that, there is no further oxidation. So the reaction is going to stop. I mean, the ketones don't get oxidized. So the first statement is wrong. So the first one is absolutely wrong. Now, 1 mole of Y gives 1 mole of triiodomethane when it reacts with an excess of alkaline aqueous iodine. So this one is known as the iodoform test. Okay, what is the iodoform test? The iodoform test, the option I'm talking about the second one. Alkaline aqueous iodine is the iodoform test. It's a test for a very specific structure. The structure is CH3 next to acetyl bond O and the rest of the molecule. Or it's a test for a very specific alcohol which should have this structure. CH3, CH, OH, and the rest of the molecule. So if the molecule has these two structures, which this one has, it has CH3 next to a acetyl bond O and then the rest of the molecule. So it's CH3, acetyl bond O. So the iodoform test is going to be positive for this. But what happens in the iodoform test is, in both cases, the same thing happens. What happens is the CH3 in both cases, it breaks away. And in both cases, it forms triiodomethane, which is a yellow precipitate. So, so triiodomethane, that gives a yellow precipitate. What happens to the rest of the molecule? That turns into a carboxylic acid. I mean, it's going to become RC double bond O. But since the conditions are alkaline, a salt of the carboxylic acid is formed. Remember, he's using alkaline with an excess of alkaline conditions. So whether if the alkali is NaOH, it's going to be the salt of the carboxylic acid. The same thing over here. This will also turn in exactly the same thing. It's an oxidation reaction. Remember, the iodoform test is an oxidation reaction. So I'll just quickly repeat that the iodoform test is for a very, very specific structure, that the molecule should have a CH3 right next to a acetyl bond O, and then whatever comes after that, we don't care. Or the molecule has a CH3 with a carbon that's bonded to an H and an OH, and then the rest of the molecule, which we don't care about. In both cases, if you add alkaline aqueous iodine, triiodomethane yellow precipitates are going to be formed, and the rest of the molecule will turn into a carboxylic acid or a salt of the carboxylic acid if the conditions are alkaline. And always remember, whenever carboxylic acid is formed, in any case, whether it's hydrolysis or esters, whenever it's formed, if the conditions are alkaline, never write carboxylic acid. It's going to form or result in the formation of a salt of the carboxylic acid. Anyway, so 1 mole of Y, how many iodoform tests could be possible in this case? So you've got CH3, CH3 next to acetyl bond O. So this CH3 will break off and it will form yellow precipitate of CHI3. This one is again CH3 next to acetyl bond O. The CH3 will break off and it will form a triiodomethane. So it's going to form 2 moles of it. So 1 mole of Y will give not one, both dono galat hai, neither one nor nor 2. So both of them are wrong. Is this clear? Yes or no? Is this clear?
Yes, sir, clear.
बस ये triiodomethane का ना ये याद रखना कि specific structures, ठीक है, it gives a positive result. ये कौन सा question था, एक second. अच्छा, where's the rest? अच्छा, just organic. 28. अच्छा, esters. This must be easy. Esters can be prepared by the reaction. Which one gives the correct names of the reagents that would be suitable to prepare? So you have to make this ester. So to make this ester, just break this ester. Figure out what's this side would be carboxylic acid. Okay, this double bond O will turn into, I mean, the original reagent must be a carboxylic acid. So it's going to be butanoic acid, 4 carbon atom. This would be double bond O and OH. So it's either B or C. And this other side will turn into an alcohol. So it's what type of alcohol is this? It's got 3 carbon atoms and there is an OH on the middle one. So this is 1, 2, 3 prop, and it's on the middle one, the second one. So it's going to be propan 2 all. So it's going to be C. Is this clear?
Yes.
So next is this compound Q can be hydrolyzed by HCl. The 2 products of this hydrolysis have the same empirical formula. So hydrolysis, who gets hydrolyzed? Esters get hydrolyzed. I mean, hydrolysis is any reaction where OH ions, or it's a reaction with water or OH ions come along. Well, for example, even this reaction was hydrolysis. Like if, किधर चला गया? एक second. Even this nucleophilic substitution reaction, if it's OH ions coming along, that's hydrolysis of a halogenoalkane. The OH will knock out the Cl and take its place. So that is also hydrolysis. Achha, esters, they get hydrolyzed. Where's our question? 1 second. Achha, so the bottom one, just a second. So compound Q can be hydrolyzed, the first one, and the two products of the hydrolysis have the same empirical formula. So again, a simple question, but you have to do all the working. The first one, you would have to draw this. It's going to be CH3, and then it's CO2. So that's C double bond O. Then another O. Then you've got CH2, and you've got CH2, and then you've got an OH. Hydrolysis with it's an acid hydrolysis. Okay, remember, be careful about the carboxylic acid thing I told you. If it had been an alkaline hydrolysis, then the carboxylic acid would not have formed. As anyways, you're getting CH3 C double bond O, OH, and this other side will be turning into a diol because there's already an OH on one side, and there's going to be an OH on the other side. As anyways, he's talking about the empirical formula. So the empirical formula is going to be, in this case, C2. H is 4 and there's O2. This one is again C2, but the H are 6, I think, and the O are 2. So they definitely don't have the same empirical formula. So what about, so again, it's just a time-consuming question because you would have to do the whole working and then you'll be able to figure out the answer. So it's CH3CO2, then you've got CH2, and another CH2, and then there's COOH. So it's going to break in the middle, and when it breaks, it ends up forming a carboxylic acid. So there's going to be an OH, and this will turn into an alcohol. As again, the empirical formula, it's going to be C2H, I think, is 4, and O2. This one is C3, H is 1, 2, 3, 4, 5, and 6. And there are 3 oxygens. So I think 3 oxygens. So I think they have the same empirical formula. I think B is correct. Is this clear?
Yes, sir.
So, I mean, you can double check this, but I'm assuming it looks like B is correct. Now, next one. That's about infrared. Remember, infrared have, I mean, by just looking at the absorption peaks, you can kind of figure out which bonds are vibrating or and absorbing infrared frequencies. So in this case, he's saying that substance T was analyzed and found to contain 62%, 10.34% hydrogen. And can somebody tell me what the empirical formula is? I mean, this divided by 12, this divided by 1, and this divided by 16. What do we get? क्या है निहाल कैलकुलेटर?
जी सर कर रहा हूँ सर कार्बन का 5 आया 5.17
Carbon 5.17 और ये क्या आ रहा है? Hydrogen is 10.34 obviously. Or oxygen is
1.724.
1.724. So now you find the simplest ratio to, I think, divide everyone by 1.724. So what do you get?
सर कार्बन का 3 आ रहा है
Okay, so you got 3 carbons and hydrogen divided by 1.724. What do you get?
5.99.
So that's 6. Or akhri, the oxygen is
that's 1
that's going to be 1, take obviously. So you're getting C3H6O. So by just looking at the formulas, I think it's there is no C3H6O, or maybe there's one. I think this is C3H6O. Yeah, but double hoga. It's going to be C6, H12, and O2. I mean, remember, it's the empirical formula. So the actual formula is going to have the same ratio. Is it the same ratio? 6, 12, and O2. Okay. So it could be either one of them, TK, because I think you don't have a molecule that's bigger than that. C9 wala, so I don't think there is a molecule that has 9 carbon atoms. So this is fine. Empirical formula works for this. What about this one? It's 1, 2, 3, 4, 5, and 6 carbons, and 2 oxygens. That's also fine. And hydrogens, that's 2, 4, 6, 8, 10, 12, 13, and 14. So I think that D is wrong because the empirical formulas don't fit
14
with this. Okay, वो clear कर लेना, double check कर लेना. I'm just doing this very quickly, so I think this is 14H. What about this one? It's got 2 oxygens, so that's fine. 6 carbons, that's 1, 2, 3, 4, 5, and 6, so that's fine. Hydrogens, that's 3, and 3, that's 6. 2 over here, that's 8, and 1 over here, that's going to be 9, and 2 over here, that's going to be 11, and this is 12. Okay, that's fine. The empirical formula fits. So what about this one? I think its empirical formula will fit. It's got 6 carbons, that's fine. 1 hydrogen, 2 hydrogen. Okay, that's 3, 4, 5, 6, 7, 8, 9, 10, and that's 11, and that's 12. Okay, so that's so the options are A, B, and C. Okay, we're done with the first empirical formula part. Now we need to figure out whose infrared is this one. Remember, you can't get a lot of information by looking at the infrared spectrum. So by looking at this spectrum, I can quite confidently say that B and C are wrong. Okay, and the reason, I'm going to give you the reason. The infrared spectrum doesn't really give you a lot of information in the first place. So what we can do is, let me just open the data booklet very quickly. So the infrared spectrum doesn't provide you with a lot of information, but a lot of times it provides you with some key points about the molecule and its structures. In this case, remember, infrared spectrum, it always, whenever you want to identify C double bond O in a structure, it gives you very clear results. And it gives you very clear results for OH as well, a lot of times. But C double bond O, it very uniquely identifies it. The other bonds, not that uniquely, like all the other bonds, they kind of have almost the same frequency of absorption. So there's a lot of overlapping going on. So you wouldn't be able to be very sure which bonds are resonating. But C double bond O has a very unique frequency around 1600, 1700. It's going to have a very strong absorption. So always, whenever you get an infrared question, the first thing is just focus on C double bond O. I mean, that is something that you can either, whose presence or absence you can identify very quickly. TK, if there's an absorption at 1700, 1600, it's a very strong absorption. You will very clearly identify that there is C double bond O present, whether it's an amide, ketone, aldehyde, or ester, or a carboxylic acid even. And if there is this absorption is missing, that means there is C double bond O absent. So 1600, 1700, if you go back, there's absolutely nothing there. I mean, look, there is no, I mean, this is the point. So that clearly means that there is no bond, C double bond O, which is why which is why B and C are wrong. So B and C are straight away wrong. And just for your confirmation, if you want to just figure out, you can't really get a lot of other information that clearly. OH has an absorption. I mean, it's got an OH, 2 OH groups. So you can just kind of confirm that OH has an absorption, just OH, not the carboxylic acid OH. I mean, these ones, the hydrogen bonded alcohols or the free alcohols, they resonate above 3200 or 33. I mean, they have this range, 3200, 3500. So you can see clearly that there is absorption happening above between 35 and 32, I think. somewhere along that point. So that must be the OH absorption. So always focus on C double bond whenever you're doing infrared spectroscopy. Is this clear?
Yes, sir.
Yes, sir.
चलो आगे फिर just the कहाँ पे है वो organic ये वाला कर लेते हैं. अच्छा, each of the compounds below is treated separately with an excess of NAB. अभी वो आ गया NaBH4. That means reduction is happening. The product of each reaction is then heated with an excess of concentrated sulfuric acid. So remember NaBH4, that's a reducing agent, and it reduces aldehydes and ketones back to an alcohol. So what it would do is, you see a double bond. Whenever you see a double bond here, it will turn into an alcohol. So this is a ketone, it will turn back into an alcohol. So the double bond will turn into a single bond and alcohols would be produced. So in all cases, there's going to be alcohols getting produced. You don't have to worry about primary or secondary or tertiary. You just turn the double bond O, whether it's a ketone or an aldehyde, back into an OH. It will always form the right type of OH. For example, if it's a ketone, it will automatically turn into a secondary alcohol. If the OH is on the first carbon, if the double bond, if it's an aldehyde, it will automatically turn into a primary alcohol. So you don't have to worry about whether you're making a primary or a secondary alcohol. Reduction automatically changes it into NOH. That's it. So then he's saying the product of each reaction is then heated with an excess of concentrated sulfuric acid. Now, what concentrated sulfuric acid does is, it's a dehydrating agent. What it does is that whenever it sees an OH, so whenever it sees an OH, the OH is gone and the H from the neighboring carbon atom, the next door carbon atom, the H is gone. And remember, it's always the next door carbon atom, not the third one or the fourth one. The OH goes from one carbon atom and right next door, the H is gone. And that results in the formation of the alkene. ठीक है. अच्छा, इसमें पता नहीं क्या कह रहा था, वो कह रहा था product of each reaction, so it's turning into an alkene. Which compound gives only one final product with the molecular formula C7H10? So only one product, and that is going to be definitely I think 2 and 3 or 1 or 2. So let's look at 1. So OH will be gone, right? अच्छा, यहाँ पे the double bond has no choice. I mean, the bottom double bond has no choice. The OH will be gone. And there's an H on the neighboring carbon atom, that would be gone. The double bond would always appear over here. Even in this case, if this OH dehydrates, the double bond only has one position. Okay, the OH will be gone and the neighboring carbon atom H will be gone. Okay, there'll be the neighboring carbon atom H will be gone. Ye clear hai? Niche wali dehydration. Okay. So wahan pe there is no choice. I mean, there's just one place where the double bond could appear. The choice is above. I mean, if the OH goes over here, तो साथ वाला H कौन सा होगा? It could be this one, or it could be this one. It's got two options. I mean, this H could be gone, so the double bond appears over here, or maybe this H goes and the double bond appears over here. So you've got two options here. So you'll get two different products. Is this clear?
Yes.
तो इसका मतलब है अगर 1 गलत है तो 2, 3 automatically correct है. ठीक है. So in this case, OH goes, you've got two options. Double bond appears either on the right side or on the left. But it's a symmetric molecule, so no matter where it appears, it's going to look exactly the same. But it's just going to be a flipped version of it. Is this clear?
Yes.
Okay. And over here as well, the OH doesn't have two options. It just has one option, which is this one. The double bond would always appear over here because if the double bond forms over here, this carbon atom no longer has any H atoms. So you can't remove an H atom anymore because you already did. I mean, there was only one H atom with this carbon atom. So that's gone. So the OH will be gone. Then it has to look for the H atom from the neighboring carbon atom. Is this point clear?
Yes, sir.
Yes, sir.
ठीक है, क्योंकि यहाँ पे ना on this side, but the H are gone. All of them are gone. So there is no H. And remember, that's one thing. Sometimes you run out of H atoms. TK, for example, this molecule will not get dehydrated. If I draw this molecule, and there's a CH3, TK, these are the 3 hydrogens. Now this molecule will not get dehydrated. The reason is the OH will be gone from the carbon atom, and the neighboring carbon atom, the H must go, but there is no H. So there isn't going to be any dehydration possible. Okay, because the OH will not be able to find the H from the neighboring carbon atom. So which is why 2 and 3 are correct in this case. As the next one is, how do you convert Y into Z? So what's Y and what's Z? Y is this tricky question. Should you react sodium with it? A carboxylic acid turns into a sodium salt. Will the reaction happen?
Yes.
Okay, it will happen, but one is wrong. Why is it wrong? I mean, this thing will happen. Okay, with sodium. It's going to happen, but why is one wrong?
क्योंकि सर वो अल्कोहल के साथ मतलब वो OH के साथ भी रिएक्ट कर सकता है वो CO2
हाँ ठीक है क्योंकि alcohols are very weakly acidic. I mean, they're almost not acidic, but they also react with sodium. So the problem would be that the OH alcohol would also react with Na. So in this case, that is not happening. So that means you can't use Na because the Na would come in this OH as well. The other ones will. I mean, these two are fine. Remember, we did discuss this in equilibria when we were studying equilibria as well. Carboxylic acids, like carboxylic acids are complete acids. They're capable of reacting with metals. They're capable of reacting with metal oxides or hydroxides, which are strong bases. And they're capable of reacting with carbonates, which are kind of weak bases as well. But alcohols, they don't have reactions with all of them. They just have reactions with sodium. That's it. They're hardly acidic. I mean, it's very hard for them to ionize or dissociate. So they hardly have any reactions at all. So the first one can't be used because the first one will react with both. You just wanted to react with the carboxylic acid part. So which is why you're going to use 2 and 3. Okay, clear?
Yes, sir.
So उसके बाद you've got 38 bromoethane undergoes nucleophilic substitution reactions. Which statements are correct? Again, it's ये halogenoalkane nucleophilic substitution. We just did that. कहाँ गया था? So we just did nucleophilic substitution. Except that this is bromoethane, so that's 2 carbon atoms and there's a bromine over here, but pretty much the same thing. So Cn-1, that's NaCN ethanolic. You've got NaOH, which is going to be aqueous, and this is going to be NH3 ethanolic plus reflux. I mean, reflux in all 3 cases. NH3 ke case mein extra ye hoga कि you can put it in a sealed tube under pressure and heat it. So that would also result in, that's also going to result in nucleophilic substitution. So coming back to this, it's the same reaction. So where's my questions? So bromoethane reacts with aqueous NaOH to make ethanol. That is true. I mean, that will happen. So there's H. The positive bromine is negative. So the OH-1 will attack that carbon atom. It's going to attack that carbon atom. And the carbon atom is only bonded to just one alkyl chain. So it's a very strong positive charge. So it's going to get immediately attracted to it. So the first one is correct. The bromoethane reacts with ethanolic NH3 to make ethylamine. That's also true. Ammonia will react ethanolic. And instead of Br, there's going to be NH2 that would take its place. The Br will get knocked out. And that would be ethylamine. That is true. Bromoethane reacts with KCN to form ethane nitrile. That is slightly wrong. Just very slight.
That's not true now.
कौन सा?
ये वाला सही नहीं है बिकॉज सी का एक और कार्बन ऐड होता था ना।
हाँ ठीक है, ये याद रखना है कि whenever KCN is bonded, तो यहाँ पे there's going to be CN, ठीक है, that's going to take its place. So instead of having 2 carbon atoms, you now have actually 3 carbon atoms. So it's going to be propane nitrile, not ethane nitrile. ठीक है, clear है?
Yes, sir.
ये CN का ख्याल रखना है, उसमें वही बेसिकली काफी हद तक सही था, except कि it's going to be propane nitrile, that's it. As a 37, following fractional distillation of crude oil, which process can be used to produce propene, a larger hydrocarbon? So propene. Which one?
Cracking.
ठीक है, that's it, cracking. मतलब large hydrocarbons, that's it, ठीक है. You just crack them, that's it. I don't think reduction say there's no reaction where reduction produces alkenes. Polymerization uses up alkenes, doesn't really produce alkenes. बाकी इसका आ गया, इसका देख लेते हैं एक W19 theory question. So let's कहाँ से शुरू हो रहा है? It's a big question. It's a W19. That's a big question. Just a second. Question number 3. चलो let's ये चलो मैं वैसे भेज दूंगा, ठीक है, कल करेंगे उसमें फिर ये कर लेंगे, ठीक है. We'll do the next one maybe tomorrow, ठीक है, clear है?
Okay, sir.
Okay, sir.
चलें ठीक है. Okay, everyone take care.
Allah Hafiz.
Allah Hafiz.